This video is going to deal with section 12.4. Section 12.4 is mathematical induction. Mathematical induction. Now, mathematical induction is a way of proving statements that are true for all natural numbers. This is a technique of proof. It's a proof technique. Now, before everybody just decides to turn off the video and say, I hate proofs, we do have to learn this. This is one of the standards, one of the California standards for precalculus is mathematical induction. It can't be that bad because when you look at your textbook, at least the book that we use, there are only 2 pages of explanation. In fact, there's not really even 2 pages of explanation. There's really only 1 page of explanation, and then the rest of it is just a couple of examples, and poof, you're into the homework assignment. So instead of thinking it's going to be catastrophic, why don't we stay a bit optimistic and think, hey, maybe this isn't going to be that bad. So what do we have to know before we can proceed with mathematical induction? Well, we have the principle of mathematical induction. And what does the principle of mathematical induction say? Well, the principle of mathematical induction says this. This is what it says. All right. It says, suppose the following 2 conditions are satisfied with regard to a statement about natural numbers. So, if the following 2 conditions are satisfied, we have proven a statement to be true by mathematical induction. Okay, so what does it take to prove something is true by mathematical induction? Well, we have to show the following 2 statements are satisfied, the following 2 conditions. First, we have condition 1. And what does it say? It says the statement is true for the natural number 1. Right? The statement is true for the natural number 1. And then the second condition, condition 2, condition 2 says if the statement is true for some number k, some natural number k, it's also true for the next natural number. So if the statement is true for some natural number k, then it is true for the next natural number. And the next natural number after k, the natural number that comes next, is going to be k plus 1. So if we can satisfy these two conditions, then we can prove something is true by the technique of mathematical induction, all right? So where do we go from here? Well, from here, we do an example, all right? So let's pick an example. Here's an example. We can begin with this one. All right? We'll begin with this. What does it say? It says we're supposed to show that 1 plus 5 plus 9 plus all the way to 4n minus 3. So if we have this series of numbers, right, 1, 5, 9, this appears to be arithmetic. The common difference here is 4. The common difference here is 4. So we have this arithmetic series. We have a series of numbers. They all have a common difference, so it's arithmetic. We're supposed to show that this is equal to n times 2n minus 1. Now, what does that mean? And what is n? Well, n is, this is the first term, this is the second term, this is the third term. So what does this statement say? This statement says, if we wanted to add together the first three terms, the first three, we would add 1, 2, and 3. So n would be 3 in this case. We would have 3 terms, so n would be 3. What this says, if we add these numbers together over here, we can do the first 3 pretty easily. We get 1 plus 5 plus 9, that's 16, right? We get 16 on this side. Sorry, that's 15, isn't it? So that's 15. They say we would get exactly the same thing. We could get that answer quicker using this formula. Now this formula only applies to 1 plus 5 plus 9 plus, what's the next number after 9, right? We're adding 4, so 13 plus 17. So if we have a series that looks like this, we could sum it quickly if we used this formula. Now we said for ours, n was 3. Let's see if it works. We get 3 here. This is going to be 2 times 3 minus 1. That's going to be 3. 2 times 3 is 6. 6 minus 1 is 5. And we get the same thing, 15. What would have happened if we would have added up the first 4 numbers, right? If we go back and we add up the first 4, it'd be 1 plus 5 plus 9. Right? We're going up by 4. 1 plus 4 is 5. 5 plus 4 is 9. 9 plus 4 is going to be 13. 13 plus 4 is going to be 17. Let's do the first 5 numbers, right? Let's do the first 5 numbers. Now let's ask ourselves, what would these add up to? Well, 13 plus 17 is 30. 9 plus 1 is 10, so that gets us 40. So these numbers add up to 45. Now this statement, the purple statement, says we could do that. We could add those up. After all, there's only 5 of them, so we could add those up. But say there were 55 of them or 75 of them. We could use this formula over here. Now remember, in this case, we have 1, 2, 3, 4, 5. So our n is 5. How many numbers are we adding up? That's what n is. So if we try the shortcut formula, we get 5. N is 5. We get 2 times 5 minus 1. So we get 5. 2 times 5, of course, is 10. 10 minus 1 is 9. 5 times 9 is 45. So the formula appears to work, right? The formula looks like it works. We could say, well, you know, it worked when I did 3 numbers. It worked when I did 5 numbers. Voila, it must work for all numbers. But that's not a proof. That's a proof that it worked for 3 numbers, and that's a proof that it worked for 5 numbers, but I don't know it's going to work for 7 or 25 or 305 or 2 million numbers. I only know it works for 3 numbers, and it works for 5 numbers. So what am I going to have to do to show that this purple statement is true? Well, this is the kind of statement that we can prove to be true using mathematical induction. Okay? So typically when we're working with mathematical induction, we use steps. I like to teach steps. So I say, okay, we're going to do step one. Right? Step one. Now, what is step one? We want to show the statement, and this is what we write on our paper. We're going to show the statement is true for, and it says right here, we have to show it works for 1. So we're going to say it's true for n equals 1. Now, what does that mean? Well, that means n is 1. So on the left-hand side, this side over here, we're only going to get one term. So the left-hand side is going to be 1. Right? It's going to be 1. That's our only term. N is 1. We only have one term. Now, that we're curious, right? We're trying to find out, is that equal to what we get over here when n is 1? Well, let's see. If n is 1, we put a 1 there. This would be 2 times 1 minus 1. If we simplify that, right? If we simplify that, what do we get? We get 1. We get 2 times 1 minus 1. That's 2 minus 1. 2 minus 1 is 1. So we get 1 times 1. That's 1. And we put a check mark next to that because we have satisfied condition 1. We have shown the statement is true for the natural number 1. We showed it's true for n equals 1. See, not that bad. Now, what do we do for step 2? Well, for step 2, we write assume the statement is true for n equals k. Now, it's really important for us to realize that up here we have the verb show. What does that mean? That means step 1, there is work to be done, right? When we did step 1, there was work to be done. We had to show the left-hand side was equal to the right-hand side. Step 2, our verb here is not show. Our verb here is assume. What does that mean? That means in this step, there is no work to be done. All right? I like to write that out so that we can remind ourselves just what is expected. What's expected in step 1? In step 1, show. Show is a verb, an action verb. So we are going to have to literally show it. We got to start with the left hand, show it's equal to the right hand. Step 2, we're simply assuming. We're assuming we don't have to show anything. We have to assume that this statement right here is true when n is equal to k. Now, what does that mean? Well, that means 1 plus 5 plus 9 plus all the way up to the kth term. The kth term is 4k minus 3. 4k minus 3. We've gone up not to the first term, not to the second term, not to the third term, but the kth term. Okay, the kth term. So we've got it written out to the kth term on this side. Now, what are we assuming that's equal to? Well, we're assuming this statement right here is true. So if it's true for the kth term, it's true then on the right-hand side when we plug in k. Now, every time we do step 2 in an induction problem of this type, this is what step 2 is going to look like. There's no work in step 2, right? No work to be done in step 2. Now, what does this condition 2 say? It says if the statement is true for the natural number k, then it follows that it's true for the next natural number. So that gives us a hint about what step 3 is going to be. Step 3 is going to say show, all right, and we know what that means. Show the statement is true for n equals k plus 1. I have to show it's true for the next natural number, right? The next natural number. The next natural number is k plus 1. Now, what does that tell us? That tells us that because our verb here is show, right? Show, there is in this step work to be done. Okay, this step has work that we have to do. Now, what work do we have to do? Well, we're going to plug in k plus 1 into this statement right here, and we're going to try to show that it's true. That's what it says. It says show that this is true. So, I'm going to go back to my original statement, the problem that I saw in my textbook that it said prove this to be true by mathematical induction. I'm going to rewrite that, but I'm going to rewrite it in a special way. Okay, I'm going to write down the first 3 terms like they showed us. I'm going to write plus. I'm going to put my dot, dot, dot. I'm going to write plus. Now, we have to stop at the k plus 1 term. In other words, we have to stop when that is k plus 1. So what's the trick? What's the important thing that I have to remember to do in a mathematical induction problem such as this one? I have to remember to write down the second to the last term. Now, I know that sounds kind of confusing, but what do I mean by that? I mean, we're going to stop. We're going to stop when we plug in k plus 1. In other words, we're going to stop right here. Here's where we're going to stop. We're going to stop when we plug in k plus 1. Okay, that's where we're going to stop. How did I know to stop there? N equaled k plus 1. So right here in place of that n, I put in k plus 1. But what's the important caveat, the important additional thing we need to remember here? The important additional piece of information we need to remember in step 3 is we want to write down the term that comes before the last one. Now, the term that comes before k plus 1 is the term that comes right next to it on the left. What term comes before the k plus 1 term? The kth term. You're correct, the kth term. So we want to write that here. What does it look like when we plug in k? It looks like 4k. So who comes after k? K plus 1. So we want to remember to put this down. Now, what are we supposed to prove that's equal to? We're supposed to prove it's equal to this when we plug in k plus 1. So we have literally plugged k plus 1 in on the left side, and we've plugged k plus 1 in on the right side, and our job is to show these two things are equal. Now, right now, when you look at it right now, it doesn't look like that's going to happen, does it? I mean, how are we going to show these two things are equal? Well, here, after writing this down, we want to remember to use step 2. Okay? We want to remember to use step 2. Now, what do I mean by that? Well, look at this. And then look right here. Look right here. 1 plus 5 plus 9 plus all the way to 4k minus 3. We know what that is. Step 2 said we're going to assume that 1 plus 5 plus 9 plus all the way to 4k minus 3, this exact thing we have right here, we're going to assume that that's equal to k times 2k minus 1. So I can replace all of this with this. Because I can substitute that in place of this. They're equal according to step 2. That's the important thing about step 2. We're going to use it in step 3. Now, what else do I have over here? I have this, right? I have 4 times k plus 1 minus 3. Now somehow, we're hoping that is equal to this. And if we look at them right now, they don't look very equal, do they? But what are we going to do? We're going to go back to our idea that we had way back in, well, the first time we probably encountered this was in trigonometry, when we had somebody on the left-hand side, somebody on the right-hand side. They did not look equal. So what did we do? We simplified the left-hand side. We simplified the right-hand side until they matched. And we can do that right here. What happens if we multiply these out, collect like terms, right? What's k times 2k? Well, that's going to be 2k squared. What's k times negative 1? That's minus k. Plus 4 times k is 4k. 4 times 1 is 4, and don't lose this minus 3 right here. Right? What does this look like when we simplify this? Well, there's only one term with a 2k squared, so we get 2k squared. Now, here we have a negative k plus a 4k, so that's going to give us 3k. And what do we get when we get 4 minus 3? We get plus 1. Now, we're really hoping that this side is going to match that side. So let's multiply it out and see what we get. Right now we have k plus 1, right? K plus 1. Let's clean this up. This is 2k. This times this is going to be 2. Right? 2 times 1 is 2. Minus 1. 2 minus 1 is 1. Well, we can FOIL this. What's 2k times k? That's going to be 2k squared, right? K times 2k. K times 1 is plus k. 1 times 2k is 2k. And then 1 times 1 is 1. Now, what do we get if we collect like terms? 2k squared plus 3k plus 1. We showed the left-hand side matches the right-hand side. And it says, if the statement is true for some natural number k, which we assumed it was, then we have to show it's true for the next natural number k plus 1. And we did that. We showed the statement was true for the next natural number k plus 1. When we plugged in k plus 1 on the left-hand side, we plugged in k plus 1 on the right-hand side. And then we simplified. We got them to be equal. So, this is what a proof by mathematical induction looks like. Once we get, in step 3, the left-hand side to match the right-hand side, then we have completed our proof. So we could say, therefore, the statement is true by mathematical induction. Now that's our first example, right? That's just example 1. We're going to do 2 more examples. The first time you see mathematical induction, you're not really sure what's going on. It kind of happens fast, and then, boom, boom, boom. Next thing you know, you're done, and you don't really have any idea why you're done. How could I possibly be finished? What did I really do? Well, what we did is we showed these 2 conditions were met. That's what we did. That's what the principle of mathematical induction demands. It says, if the following 2 conditions are satisfied, we have proven a statement to be true by mathematical induction. So we showed these 2 conditions were satisfied. All right? So let's do another example. We'll do another example. It's going to look very similar to this. All mathematical induction problems, well, most mathematical induction problems look very similar to this. The problems we're going to address in our class, they're all going to work out like this. We start with step 1. We show it's true for 1. That's a work step. Then we go to step 2. We assume It's true for some natural number k. There's no work here. All we do is write down what that means. Then we move to step 3. Step 3 is a show step. We have to do work. We have to show these two sides are equal. And we use step 2 in step 3. All right? So let me erase this. We'll do another example. Every time I'm erasing this, I always feel like I should be asking, do you want double rice? All right, there we go. So let's look at another example. All right, you can't do too many examples, so we'll do another example. What does this one say? Well, this one, right, let's see what this example says. It says, what happens if I take 1 plus 3 plus 3 squared plus 3 cubed plus all the way up to 3 to the n minus 1. So this is our first term, our second term, our third term, our fourth term. This is our nth term, all right? Let's write that underneath here just so we can follow along and make sure we understand what I'm saying. Our first term is 1, right? That's a sub 1. Our second term, right? This is a sub 1. Our second term is 3. Our third term is 3 squared. Our fourth term is 3 to the third. See how the power is 1 less than the term we're talking about? All right? Fourth term, 3. Third term, 2. Second term, 1. And this, of course, is 3 to the 0. 1 less than 1 is 0. So this is a sub n out there. That's our nth term. Now, the problem says if you were to add all of these up, you would end up with the same thing you could have gotten a lot quicker by taking 1/2 times 3 to the n minus 1. All right? And the instructions say, prove this by mathematical induction. All right? Prove it by mathematical induction. So, how are we going to proceed? Well, we could do what we did last time, right? We could check to see if it makes any sense. We could check to see, well, what happens if we add the first 3 terms together here, right? What do we get? That's 9. 3 squared is 9, plus 3 is 12, plus 1, 13, right? We get 13. Now, we added together the first 3 terms, so we should get the same thing, right? Same thing over here when we plug in 3. N is going to be 3. There were 3 terms, so n here is going to be 3. What do we get here if we plug in 3? We get 1/2. We get 3. N is 3 this time. Minus 1. That's going to be 1/2 times 27 minus 1, which is 1/2 of 26, which works out to be 13, the same number, right? So again, that's not a proof. We can't call that a proof. That's not acceptable. We can't say, well, it worked for the first 3 numbers, so it's going to work for every number. No, that's not a proof. That's just a check. So what do we have to do? We're going to do the same thing here we did in our previous example. Same thing, right? That's the great thing about math induction. It's the same 3 steps every single time. So what was step 1, right? You can look back at your notes. You can see what step 1 was. Step 1 said, show, right? Show true for n equals 1. We have to show it works for the first case, show it's true for n equals 1. So remember, now this is a work step, right? This is a work step. We have work to be done. Doesn't hurt to write that in when you're doing the problem. Why? Because show is an action verb, so we have work to be done. What work are we going to do? Well, we're going to plug in 1 over here. We're going to use 1 as n on this side. Now, if n is 1, that means I only have my first term, so this side's just going to be 1. And now we're hoping, right? We're hoping, I wonder if that's going to be equal to get what I, to what I get when I plug 1 in on this side. What do we get when we put 1 on that side? We get a half. We get 3 to the first, right? N is 1, so we're going to put a 1 there, minus 1. Now, what does that work out to be? That works out to be a half times 3 to the first. 3 to the first is 3, so that's 3 minus 1. That's going to be 1 half times 2, and that's going to be 1. So we did what we said we were going to do. We showed it was true for n equals 1. That was step 1. That's always step 1. Unless in the problem they say, hey, this formula doesn't start working until n is, maybe it says this formula doesn't start working until n is 5. Well, then you wouldn't start with n is 1. You would start with n is 5 because they've already told you the formula doesn't start working until you get to 5. But in our problem, they didn't put any limitation out here, so we start with 1. Right? And remember, step 2 is our assume step. We're going to assume the statement is true for n equals k. Now, what does that mean? Well, now remember, this is a no work to be done step, right? Assume is not an action word in the sense that we have to complete any work. We're just going to rewrite this, rewrite our green statement with k. We're going to show it's true when, or we're going to assume it's true. So what do we know? We know 1 plus 3 plus 3 squared plus 3 cubed plus all the way up to what I would get if I plugged in k. All right? I'm assuming that's equal to this. Okay? It's equal to this. Now we're done with step 2, right? That's the great thing about step 2. Step 2 is just assume. It doesn't say to do anything. We just rewrite our given problem assuming the n has been replaced with k. Now we're going to need that. We're going to need this in step 3. So let's write down step 3. What does step 3, remember what step 3 says now. Step 3 says show, right? The statement is true for n equals k plus 1. Our second condition said if the statement is true for an integer, we called that integer k, then it must be true for the next integer. So the integer that follows k, the next integer is k plus 1. Now remember, this step has work to be done, right? Work to be done for this step, because our word here is to show. So what are we going to do? If you remember the previous example, we're going to rewrite this. We're going to go all the way to the k plus first term. We're not going to go to the kth term. We're going to go to the next term. So we're going to get 1, right? 1 plus 3 plus 3 squared plus 3 cubed plus. Now, just like in the previous example, it's very important that we remember we want to write down not just the k plus first term, not just the term we get by plugging in k plus 1, but we want to write down the term we get by plugging in the number that comes before k plus 1. So, what do we get if we plug in k plus 1 here? That would be 3 to the k plus 1, right? We're putting k plus 1 right here for n, so don't forget it would be k plus 1 minus 1, right? But it's so important that we remember not just to write down the last one, but write down the term that comes right before that. What term comes before k plus 1? The kth term. So what does this look like when we plug in k? It looks like this, right? K minus 1. Now what is this side going to be? This side is going to be 1/2 times 3. We're plugging in k plus 1, so that's going to be a k plus 1 up there for our exponent, minus 1. Now, this is a show step. Step 3 is a show step. We want to show that that side over here, the left-hand side, is equal to the right-hand side. And when we look at it, we say to ourselves, well, they don't look very similar. And of course, you're right, they don't. But we have that same situation we had in the previous example. We have here 1 plus 3 plus 3 squared plus 3 cubed up to 3 to the k minus 1. And if we look at step 2, we knew when we were writing step 2, we were going to need to use that in step 3. If we look at step 2, we know what 1 plus 3 squared plus 3 cubed all the way to the 3k minus 1 is. We know that's equal to 1/2 times 3 to the k minus 1. Now what do we have right here? We have plus 3 to the k. I'm going to simplify that. K plus 1 minus 1 is just 3 to the k. So we have plus, right, plus 3 to the k. Now, supposedly, that's going to equal the same thing we have over here. That's what we're hoping, right? That's what we're hoping. So our job here is to show that the left-hand side, I'm going to change pen colors because that blue pen is dying, to show that the left-hand side is equal to the right-hand side. So how are we going to do that, right? What are we going to do over here that's going to help us move from this side to this side? Well, let's see what this looks like. What does this look like if we distribute the half, right? What does it look like? Well, we would have 1/2 times 3 to the k. That would be 3 to the k divided by 2, wouldn't it? What's 1/2 times negative 1? That would be minus 1/2. And what do we have here? We have plus 3 to the k. All right. Now, when we do mathematical induction problems, we get to do some very interesting algebra. And this is one of those cases where we get to do very interesting algebra. I'm going to rewrite this. I'm going to rewrite this now, and let's see if we can follow along on what's about to happen here. Right? We're hoping that's going to be equal to this. Let's rewrite this. I took 1/2 times 3 to the k, and I correctly expressed that as 3 to the k over 2. But I'm going to go back now. I'm going to go back and I'm going to think to myself, you know, maybe there's a better way of writing that. Maybe it's better if I write that as a half times 3 to the k. Now, why is that better? Well, I'll show you. I'm going to move this over here next to it. But I'm going to write 3 to the k. 3 to the k, I'm going to write 3 to the k like this. I'm going to write it as 1 times 3 to the k. Now, we can put a 1 in front of anybody, right? We can put a 1 times 3 to the k is clearly the same as 3 to the k. Now, I'm going to put the minus 1/2 here at the end. And that's 1/3. So we'll erase that. We'll say minus 1/2 right there. Now, take a look at these. Take a look at these. We're going to do some interesting algebra here. We're going to factor out a 3 to the k. We're going to factor out a 3 to the k. Okay, what's left if we factor out a 3 to the k? We have 1/2 plus 1. Now here's my minus 1/2 right here. Okay. Remember, we're hoping this is going to equal this over here. What is 1/2 plus 1? Well, that's 3 to the k times 3 over 2, isn't it? Minus 1/2. Is it 1/2 plus 1, 3/2? What happens if I now multiply the 3 in there? Sorry, the 3 to the k. What happens if I just multiply these two together? What do I get? Well, don't I get this? I get 3 to the k times 3 divided by 2 minus 1/2. True? Isn't that what happens? But look at this. That's 3 to the 1. What's 3 to the k times 3 to the 1? Right? Don't we have a rule? Don't we have a rule if you have a number to the n times the same base to the m, that's a to the n plus m? Isn't that our rule? Isn't that what it says? So let's take this, right? Let's take this, and let's continue over here. What does this equal? If we do this arithmetic, right, this exponent rule right here, that says 3 to the k times 3 to the first, we add the exponents. That's 3 to the k plus 1 all over 2. Minus 1/2. Now let's factor out 1/2. If we factor 1/2 out of here and 1/2 out of here, that's going to put 1/2 out in front. It's going to leave me a 3 to the k plus 1 right there. And 1/2, that turns into a minus 1. And we have reached a matching point. Our left-hand side matches our right-hand side. And we said if the left-hand side of step 3 matches the right-hand side of step 3, then we have proven this to be true by mathematical induction. If we do step 1, and we do step 2 and 3, and we get step 3 to work, then this is true by mathematical induction. Now, this problem, right, this problem's a little different than the problem we did for our first example. This problem has this step in it right here. I'm going to circle it. I'm going to put a purple box around it. It has this step. This idea of where do I go to get my k plus 1, right? How do I get my 3 to the k plus 1 when I only have a 3 to the k? Well, I get a 3 to the k plus 1 by remembering, right? By remembering this. 3 to the k plus 1 is 3 to the k times 3 to the first, or it's 3 to the k times 3. That algebra comes up quite often in proofs using mathematical induction. This algebra of exponents. We're going to see this quite a bit in the homework, so we want to keep this in mind. If we get to the homework and we get confused and we get to one of these steps, we can come back, rewatch the video, listen again, take better notes this time maybe, and then go back and try the homework a second time. All right? So let me go ahead and get rid of this. Let's go ahead and get rid of this. You guys all got my double res tempora joke earlier, right? Okay. I didn't say it was a funny joke. I just said it was a joke. As my students will tell you, most of my jokes aren't funny. They're still jokes. They're just not funny jokes. All right. Let's try one more example. Okay, one more. We'll pick something that looks maybe, maybe a little bit worse. None of these are worse than any of the other ones. They all require the same 3 steps. We can work them out in usually about the same amount of work on a piece of paper. There's not a lot about these problems to panic about. If we can remember our 3 steps and just keep track of what we're doing, we can usually get our math induction problems to work out pretty well. So what does this problem say? This problem says 1 cubed plus 2 cubed plus 3 cubed all the way up to n cubed is equal to 1 over 4 times n squared times n plus 1 squared. Okay. Now we had a formula back in, I think it was section 12.2 that told us 1 cubed plus 2 cubed plus 3 cubed all the way up to n cubed equaled n times n plus 1 all over 2 squared. That's what we said. And that's what this is. This is n times n. We wrote it like this in our notes back in 12.2. We wrote it as n times n plus 1 all over 2 squared. I don't want you to think we're looking at a different formula here. I don't want you to think, wait a minute. Back in my notes in 12.2, I thought this equaled something else. Well, it didn't. It equaled exactly this, but we wrote it like this. That's the only difference. That's the only difference. All right. So where do we go from here? Yeah, you're right. We start with step 1. Show, and I'm gonna abbreviate now. Instead of say show the statement is true, I'm just going to save time. I'm going to say show true for n equals 1. Now remember, that means we only have one term. N is 1. We have one term. So we're hoping that 1 cubed, that's my first term, we're hoping that's going to be equal to what I get over here when I plug in 1. So what do I get over here when I plug in 1? I get 1 squared, and I get 1, right? N is 1, so I get 1 plus 1 squared. So what does that turn into? Well, that turns into 1 squared, which is 1. 1 plus 1 is 2, so that turns into 4 divided by 4, which is 1, and we showed it's true for n equals 1. Now remember, our verb here is show. So this is a work to be done step. Right? It's a work to be done step. What about step 2? Well, now remember, step 2, we don't have any work, right? We just write it out. Step 2, assume the statement is true for n is equal to some integer k, right? Now, remember, for us, this step is no work to be done. Because this step doesn't say show, it says assume. So what do we do here? We write down what this would look like if we replaced n with So the left-hand side would be 1 cubed, 2 cubed, 3 cubed, all the way to k cubed, right? Because we're replacing n with k. And so what would that equal then? It would equal 1/4, wouldn't it? 1/4 k squared times k plus 1 squared. There's no work to be done in step 2. Step 2 is finished. We assumed it was true, so there's no work. Now we get to step 3. This is where, as I'm sure you've noticed in the previous 2 examples, this is where all the work comes in, right? Step 3, we want to show, so it's a do step again, right? Work to be done. Show true for n equals k plus 1. So we're going to replace n with k plus 1. Now what is that going to look like? Well, we're still going to have 1 cubed at our beginning, and then we're going to have 2 cubed, and then we're going to have 3 cubed. And we're going to end with k plus 1 cubed, right? K plus 1 cubed. But remember, yeah, I see, yeah, that's good, you're doing it. Remember, on the third step, we write down k plus 1, but we want to write down the term that comes before that one, don't we? What term comes before k plus 1? Yeah, the one before that, k. So this is going to be k cubed here. Now what is this supposed to equal? It's supposed to equal this with k plus 1 in it. So I'm going to put a k plus 1 there in place of n, right? N equals k plus 1. So in place of n, I'm going to put a k plus 1, I'm going to square it. And then over here, I'm going to put a k plus 1, right? That's k plus 1 plus 1 squared. Now, I bet some of you are already working ahead. This is a show step, right? So there is work to be done, isn't there? And you already know what you're going to do. You're going to highlight this, and you're going to say, hey, I already know who that is. I wrote that down in step 2. In step 2, I wrote 1 cubed plus 2 cubed plus 3 cubed all the way to k cubed. I know exactly what that is. That is equal to, I can replace that with what I wrote it as in step 2, pardon me. So that's 1/4 k squared times k plus 1 squared, right? And then I have plus k plus 1 cubed. So where did that k plus 1 cubed come from? That came from right there. Now we want that to be equal to this side. What is this side? This side is 1/4, right? K plus 1 squared times k plus 2 squared, isn't it? Now what are we going to do? How are we going to get the right-hand side to match this left-hand side? How are we going to get this side to match this side? Right? What are we going to do there? Well, one thing we could do, right? We could look at this and we could say, well, you know what? Okay, hold on. There's a k plus 1 squared here. There's a k plus 1 cubed here. I could factor out a k plus 1 squared. Here's a k plus 1. So maybe I could take out a k plus 1 squared. Now what does that leave me when I do that? When I take a k plus 1 squared out of here, right? When I take a k plus 1 squared out of here, I'm going to have a 4th left, aren't I? I'm going to have a 4th. And I'm going to have a k squared. I'm going to have a k squared. What are we going to have over here when we take out a k plus 1 squared? Well, we have 3 of them. If we take out 2, we're just going to have k plus 1, aren't we? Just k plus 1. Now, right now, we have a k plus 1 squared, and we have a k plus 1 squared over here. That's all that match. So what else could we do? Well, we could pull a 4th out of here. And if you're thinking to yourself, how am I going to take a fourth out? There's not a fourth in there and there's not a fourth in there. Yes, there is. There really is, right? Because think about this. K is equal to 4 over 4K. Now take a look at that because this is 1, right? And that's what 1 is. So we could rewrite that as 1/4 times 4K. So I could take a 1/4 out of 1K and I'll be left with 4Ks. What about the 1? Well, could we play the same trick? Is 1 equal to 4 divided by 4? Could I take a 1/4 out of this and write this as 1/4 times 4? So we do some interesting algebra when we get to mathematical induction. And if you don't like what I'm doing right here, don't worry. I'm going to show you another way to do this problem just in a second. This is the factoring way to do the problem. Okay? So I'm going to take out a 1/4. What does it look like when I take out a 1/4? Well, I have my k plus 1 squared still sitting out here. What is this going to look like? I'm going to get a k squared. Right? I'm going to get a k squared. So I took the 4th out. Now we know what happens when we take 1/4 away from k. When we factor a 1/4 away from 1k, we get 4k left. When we factor a 1/4 away from a 1, we get a 4 left. Look at that. Look what that is. Right? Look what that is. That's k plus 2 times k plus 2. Yeah, I see it. I see it too. What I see it. It's good. I like it. I like your excitement. That's k plus 1 squared times k plus 2 squared, and we matched this side, so we proved our statement is true by induction. Now, this proof that we did right here, this used some fancy factor. We had to factor a 4th out of there, which was really easy because there was a 4th. Then we had to factor a 4th from 1. And we had to factor a 4th from 1k. Now maybe we can follow that. Maybe that went by a little too quick. You could watch the video again. I explained it. Maybe if you watch it again, I'll explain it exactly the same. Who knows? Maybe the next time you watch a video, I'll explain it differently. If that happens, don't tell anybody. What could we have done, however? Let's just erase this. Let's say you didn't like the fancy factoring approach. Right? We didn't like that. We weren't a fan of that. So what could we do instead of that? Right? What's another choice? Well, to be honest with you, another choice. Well, let's go ahead and make that a 3 again, huh? Another choice. I mean, this is another choice. It works. You just multiply out both sides and hope they match. I mean, you just multiply them out. You multiply them out. What do I mean by that? I mean, you multiply these out. This is going to be what? It's going to be 1/4 k squared. K plus 1 squared is k squared plus 2k plus 1, isn't it? Now, k plus 1 cubed, we know what that is. That's k cubed, right? K cubed. Because this is Pascal's triangle, right? We have 1, and then it goes 1, 1, 1, 2, 1, 1, 3, 3, 1. This is our cubic line, right? This is our cubic line. I use this line right here for our squared, right? That's 1, 2, 1. That's our coefficients. So we get 1k cubed plus 3k squares plus 3k to the first plus 1. That's what we get when we cube that. Now, what does this look like? Well, let's keep multiplying and see what we get. I'm going to leave the 1/4. Well, I'm going to leave the 1/4 out here just for a second longer. What's k squared times k squared? That's k to the 4th, isn't it? What's k squared times 2k? That's 2k cubed. What's k squared times 1? That's k squared. Now, over here we have a k cubed, a 3k squared, 3k, and a 1. Now we just collect like terms. So what do we have? We have 1/4 k to the 4th plus 1/4 times 2 is going to be 1/2, isn't it? 1/2 k cubed. And this is going to be 1/4 k squared. This is going to be k cubed plus 3k squared plus 3k plus 1. Now we just collect like terms. How many k to the 4th do we have? We have 1. Right here. This is it, the only term, so we got 1/4 k to the 4th. How many k cubes? So we have 1/2, and we have 1. All right, so that's 1.5. So that's 3/2 k cubes. How many k squareds? We got a 4th, and we have 3. Now 3 is 12/4, right? Isn't 3 12/4? 3 is equal to 12/4, right? So we have 1/4 plus 12/4. That's going to be 13/4 of our k squares. How many k's to the 1st do we have? Well, we have 3 of them. And we have a 1. So instead of doing the fancy factoring, we could have just multiplied it all out, gone crazy with our Algebra 1 skills, collected like terms. Now, how do I know if it matches this? Well, I'm going to multiply that out. What is this going to equal? Well, in about an hour we'll know. It's going to be 1/4. That's k squared plus 2k plus 1. We know what that is. We just had it written on the board a second ago. That's k squared plus 4k plus 4. Now what are we going to do? We're going to distribute. We're going to get 1/4. K squared times k squared is k to the 4th. K squared times 4k is 4k cubed. K squared times 4 is 4k squared. We're not done. We got to do the 2 now. 2k times k squared is 2k cubed. 2k times 4k is 8k squared, isn't it? 2k times 4 is 8k. We're not done. We have to do the 1. 1 times k squared is k squared. 1 times 4k is 4k. And 1 times 4 is 4. That fancy factoring thing is not looking so bad now, is it? All right, let's collect like terms and see what we get here. We get 1/4, right? There's only 1k to the 4th, so we'll write that down. What do we have for k cubes? We have 4, right? 4 of them. Plus 2, that's 6, right? So we have 6 k cubes. What do we have for... Where did that come from? K squared, that's supposed to be 4k squared. Glad you guys saw that. All right, so what do we have now? We have, how many k squareds? We have 4 plus 8, that's 12, plus 1 more is 13k squares. How many k's do we have? Well, we have 8 plus 4, that's 12. And we have a 4. Now we're not done, right? We're not done. This doesn't match this yet. We got to multiply through by the 4th. That gives me k to the 4th over 4. That's good. I wanted that. What's 6 divided by 4? Well, 6 divided by 4 is 3 divided by 2, right? I wanted that. This is going to be 13k squared over 4. Hey, we wanted that. And this is going to be 12 divided by 4. That's going to be 3k to the 1st. We wanted that. 4 times 1/4 is 1. And we're done that way too. Look at that. It worked both ways. So, you are now ready to go out and tackle mathematical induction. Remember, you have more resources at your disposal. You have this video. You can go back and watch it as many times as you want. There are plenty of other videos on the internet. You have your textbook, right? So with those 3 sets of resources, you can be successful at mathematical induction. I understand that's a lot of symbols. I mean, there's a lot of symbols written down right there. That doesn't mean you can't do it. Right? Just because there's a lot of symbols written down on your paper doesn't mean you can't do the work that's associated with those symbols. So take your time, review the video, watch it more than once, read the book more than once, and you too can become competent and even better than competent at mathematical induction. All right, everybody have a great evening.